So to begin with introduction, see, virtually every phenomena in nature, whether it may be a mechanical, biological, or geological, can be described with the aid of laws of physics. In terms of what? Laws of physics, in terms of algebraic differential and integral equations relating to various quantities of interest. See, where I have interested, those areas are defined with laws of physics in terms of algebraic equations or sometimes differential and integral equations. So solving those differential and integral equations, I'll be knowing what is the solution of my interest. Okay, so where I have required those particular interest areas I can solve. Okay, so that is just one sentence introduction I have given here. Then begin with the definition. So FEM is a numerical or mathematical model for finding the approximate solution. See, I am using the word approximate solution here uh, because as I told, why I am using approximate solution, because I have mentioned in the bracket for complex bodies. See, for complex bodies, it will give you the approximate solution. Suppose I have a standard body, like I have equations for the standard shapes, like it may be a square, rectangle, circular, triangle. So if that shape of the body is there, then it will give you the exact solution. Only approximate solution you will get it when it is a complex shape body. Because in FEM, what happens? It will try to make this complex shape body nearer to the what the standard shape, so that whatever the solution I am getting, it is what the approximate solution, but it is acceptable. So to begin with the definition, FEM is a numerical technique or it's a mathematical model for finding the approximate solution to a boundary value problem. See, as I told, this word should be important, boundary value problem, because without boundary condition, FEM doesn't solve the problem. Uh, for the boundary value problems, by solving the ordinary and partial differential equations. So by solving those ordinary and partial differential equations to a boundary value problem, I can get a solution. And if it is a complex body, I will get a approximate solution. If it is a standard shape body, I will get a exact solution. So that is what the definition of this FEM. Now to begin with the basic steps involved in FEM. So as Samarth put some of the points about basic steps involved in FEM, I'll just go with the step by step. See, many books will give many different procedures, but there are 6 main basic steps which are involved in FEM. So those main 6 basic steps I am giving. Whatever other steps, they are the either sub step of any of these 6. Okay, so first one is a discretization of given continuum, where continuum is nothing but a body. Discretization is nothing but it is dividing the given body into smaller region, and those smaller region we are going to call it as an element. So that is what is the first step in the FEM, to divide the given continuum into smaller region, and those smaller regions what we call it as an element. Say for example, if I have a body, so let us assume that this is my body. Now I have to get the solution for this body. So what I need to do in FEM? So in this FEM, I have to divide this body. Body is nothing but continuum. Continuum is nothing but body. Okay. Now what I need to do? I need to divide this body into smaller region. So this is how I am dividing the body into smaller region. This is how I will divide. I'll come to that, how I have to divide the body. So this is how I am dividing the body, because it's a two-dimensional body, because my screen is two-dimensional, therefore I can able to draw a two-dimensional body here. So this is the body which I have divided, and this one portion is what we call it as an element. This is what we call it as an element, and each element is associated with the nodes. Now what are nodes here? These are the corner points of an element. See, if I enlarge this portion, so this is my element, and the corner points of these elements, what we call it as? We call it as what we call it as? Yes, those corner points of an element we call it as nodes, and the shape of the element is mainly depends on the location of the nodes. If any location of the node changes, the shape of the element changes. See, here I have 4 nodes. See, I can put 4 nodes like this. So joining these 4 nodes, I'll get this is the shape of the element. Similarly, I can put 4 nodes like this also, and by joining this 4 nodes, I'll get the shape of the element. See, the shape of the element is truly based on what? It is truly based on the location of the nodes. If any location of the node changes, the shape of the element changes. Are you following this? Now the question comes, then how to divide the given continuum? See, in the nature, some of the bodies, they are one dimensional, or actually you have to start with 0 dimensional. Some of the bodies, they have 0 dimensional, like a point. Here example, what I am going to consider it as a point. Some of the bodies, they are one dimensional, that is what we call it as a line. And some of the bodies, they are 2 dimensional, we call it as area. And some of the bodies, they have 3 dimensional, that is what we call it as a volume. Are you following this? Are you following? See, whatever the bodies or objects which are available on the earth, either they fall into the category of these 4. Either it may be 0 dimensional, or it is 1 dimensional, 2 dimensional, or 3 dimensional. But most of the whatever the elements which are available on the earth, they are in the form of 3 dimensional. Only very few are there 2 dimensional, and very rare are there in 1 dimensional. But very rarest are there in the 0 dimensional. But most of the elements which are available on the earth, they are in the form of 3 dimensional. You take any element which is there on the earth, it is in the form of 3 dimensional. Are you following this? Now, if I have a body which is of 1 dimensional, then I have to use the line element. I have to use the line element to divide that body. If I have 2 dimensional, then I have to use the area element to divide that body. See, as I have shown here, this is my 2 dimensional element because it is having a dimension in the x direction, and it is also having the dimension in y direction. So when I have such a body which is having a dimension in x and y direction, then I have to use the area element, and that area element we call it as an 2D element. Suppose similarly, if I have a body which is having the dimension in all the 3 directions, say for example, this is the body which I have a dimension in all the 3 directions, x, y, z, then I have to use the volume element. Why it is called volume element? Because length, width, and depth will give you the volume. Therefore, we call it as a volume element. And sometimes this volume element is also called as 3-dimensional element. And some of the commonly used the 2-dimensional element, very commonly used 2-dimensional element is rectangle and a triangle. So these are the 2 commonly used. Say such there are many other 2-dimensional elements are there, like I have a trapezium, I have a wedge. Okay, so like this I have different 2-dimensional element, but these are the 2, that is triangle and rectangle. So triangle and rectangle are the 2-dimensional elements which are very commonly used. Similarly, when I come for the 3-dimensional, like that I have many 3-dimensional element, but the very commonly used 3-dimensional element is hexahedron. So this is what we call it as an hexahedron and tetrahedron. What is tetrahedron? So these are the 2 commonly used 3-dimensional element, that is volume elements, which is having some volume. So if any body which is 2-dimensional, either I will use a rectangular element or a triangular element to divide that body. If it is a 3-dimensional element, I will use either a hexahedron or I will use a tetrahedron to divide that body. Are you following? This is how the discretization of given body is done initially. That is the first step in the FEM. Correct? Any doubt in this? Anybody is having any doubt? See, whatever the doubt, you try to ask your doubts. Are you following up to whatever till now I have explained? Everyone followed?
Yes, sir.
Shall I go to the
Yes,
next
sir.
step? Shall I go to the next step?
Yes, sir.
Okay. See, what is my second step in the FEM is to assume a trial displacement function. Now, what is this trial displacement function? Sometimes it is also called displacement model. Now, why we need to assume this trial displacement model? See, that is what I explained here. See, for the continuum discretized into number of elements, the displacement variation over the each of the element is unknown. Hence, a displacement function is assumed for each element. This function is called displacement model. Say, for example, when I come to the previous step, say, for example, this is a body which is I am going to fix at this end and I am going to apply the force at this end. I am going to fix this body, I am going to fix it on the left hand side and I am going to apply the force on the right hand side. Are you following this? Yes? Now what happens?
Yes,
See,
sir.
whatever the displacement which is there in this element, for example, I am telling here it is fixed and force is applied at this end. So whatever the displacement which is there in this element is different from the displacement which is there in this element. Am I right? Or whether the displacement is same throughout the body? First you tell me that. Whether the displacement is same throughout the body? Okay, I'll put in another way. Where you'll get the minimum displacement and where you'll get the maximum displacement in this body? Where I have fixed end, there I'll have minimum displacement, and where I have applied force at the free end, there I am having the maximum displacement, right? And how the displacement varies? See, it is minimum displacement, or you can say zero displacement at the fixed end, and this displacement varies to the maximum on the other end, correct? No? And it will reach the maximum at the free end. That means the displacement which is there in this element is different from displacement which is there in this element, and once again the displacement in this element is different, the displacement in this element is different, therefore the displacement at each element it is a different value. Correct? No? Am I right? Okay, have you understood this? See, displacement at each element is different. Therefore, when you come to the second step, here I need to assume a displacement function for each of the element. Say, for example, here if I have 50 elements, let us say this body I have divided with 50 elements. If I say this body is divided with 50 elements, then I have to consider 50 displacement functions. Why? Because I don't know what the displacement at this element, I don't know what the displacement at this element, I don't know what the displacement at this element. So I have to consider the displacement function for all the elements what the body is divided. And to consider that displacement function, we have two different kinds of considering the displacement function. One we call it as a polynomial function, and another one we call it as a trigonometric function. So these are the two functions we are going to consider for each of the element what the bodies get divided. Now, what is the meaning here? Let us say u is the displacement which is there in one element. Let us consider u1 is the displacement. Are you following this? Are you following?
Yes, sir.
Yes, sir.
See here, let us consider this is my first element, this is my second element, this is my third element, this is my fourth element, so on. Let us say this is my 50th element. So for each element, I will assume a displacement function. How? I will assume a displacement function either in terms of a polynomial function or in terms of a trigonometric function. So let us go with polynomial function first. So u1 is the displacement which is there in the first element. Similarly, u2 is the displacement which is there in the second element. So on, u50 is the displacement which is there in the 50th element. Are you following this?
Your voice.
That means I have to solve these 50 equations to get the displacement. And when I combine all these displacement of the each, I mean whatever the elements of each element displacement, whatever the displacement of each element, if I combine, I am going to get the total displacement which is there at the free end. That is the intention here. Are you following this? See, what I am trying to do here is I am dividing the body into smaller region and I am trying to get the value for that smaller region, nothing but element. I am trying to get the value for a particular element. Then I am adding all such elements to get the final value. Yes, is it clear? Is it clear? Similarly, if I come for the trigonometric function, this
Yes,
is
sir.
how you have to consider the trigonometric function. Similarly, u1, u2, u3 up to 50 elements, 50 equations. If it is 10 elements, 10 equations. Okay. So these are the two ways to assume the displacement function, or it is also called displacement model, or sometimes it is also called interpolation function or interpolation model. Okay. So that is my second step. Now coming to the that's what here in the same second step, out of these two functions, either polynomial or trigonometric, the one preferred for FEM is polynomial function because it is something like an algebraic equation where we can solve these equations very easily compared to the trigonometric function, because sometimes what happens, this displacement u I have to differentiate, that is du by dx. Now when I differentiate, just think, I have to differentiate a polynomial function. If I want to differentiate now, it will become very easy. How to differentiate this? A naught is constant 0 plus differentiation of a1 into x is a1 plus differentiation of a2 x square is 2a2x. So like this, differentiation of these functions becomes very easy. Suppose sometimes I have to differentiate twice, d square u divided by dx square. So I have to differentiate this u twice. Sometimes I have to differentiate it thrice. So then it becomes very easy if I consider a polynomial function. But when I consider a trigonometric function, it becomes something cumbersome because two times differentiation of this, if it is a sine, it will be get converted to cos. And when once again differentiation, that cos will be get converted into minus sign. So all those tedious process you need to use when I use the trigonometric function. See, when I am solving the problem, I'll just compare if I consider a polynomial function, how it will be, and if I consider a trigonometric function, how it becomes somewhat tedious. So I am not saying that it is not possible, but it becomes somewhat tedious process. Therefore, usually we'll try to consider a polynomial function while assuming a trial displacement function. But please remember, sometimes in the problem, she will clearly mention that assume a trigonometric function. Solve the problem by assuming a trigonometric function. Then you have to assume the trigonometric function. At that time, you cannot assume a polynomial function. Of course, if you assume a polynomial function for that particular problem, you will get the correct answer. There is no doubt, because either you can consider a polynomial function or trigonometric function, the solution will be same. There is no change in the solution. But if he mentions you to consider a trigonometric function, you have to consider a trigonometric function. If you solve a polynomial function, the marks will not be given. Are you following this? Yes?
Yes,
Shall
sir.
I move to the next? Okay. The third step in FEM is to calculate the element stiffness matrix. Say, as I divided body with number of elements, so each element having its own stiffness matrix. So I have to calculate that stiffness matrix. So how to calculate that stiffness matrix? It is by using the principle of minimum potential energy, or directly you can use that Hooke's law. So this is what the equation I obtained from Hooke's law. Say, this FEM always deals with in the form of matrix. FEM always deals with the form of matrix. I'll tell you why. Now, this is what my equilibrium equation. This is what we call it as an equilibrium equation. Now, where I obtained this equilibrium equation, it is the equation I obtained from the Hooke's law. How? The force is directly proportional to the extension in the spring. After removing this proportional, I am going to get a proportionality constant, that is spring stiffness, that is K into X. Now, instead of X, now here I have considered the displacement in the form of U. Therefore, my F will be equal to K into U. So this is how we have obtained the equilibrium equation here from the Hooke's law. So my F will be equal to K into U, where I written here where Ke is element stiffness matrix, because I am doing for the element here. For each element, I have an element stiffness matrix. UE is the nodal displacement which is there in the element. Then Fe is the nodal forces, the forces which are applied on that particular node will become my force on the node. So this is the third step where we have to calculate the element stiffness matrix. So in short, we call it as an ESM. It is a calculation of ESM. Then coming to the fourth step, this is what we call it as an GSM, or what we call it as an GFV for force. If I add all the forces, it will become a GFV. If I add all the element stiffness matrix, it becomes a GSM, that is global stiffness matrix. This is also called overall stiffness matrix. Now, what is this overall stiffness matrix, or it is also called global stiffness matrix? So as I mentioned here, see in the diagram, I have different elements here. For each element, I have ESM, that is element stiffness matrix. So to get the solution, I have to add all the element stiffness matrix. If I add all the element stiffness matrix, I am going to get the global stiffness matrix. That is what I am trying to say here. That is fourth step. So after ESM, I have to do the GSM. I have to add all the element stiffness matrix. So that is what I have given it by K. See, try to differentiate between this K and this K. This Ke, it is for the element. This only K, it is for the entire body. This is for the single element in the body. This is for the entire body, where K is equal to K1 plus K2 plus K3 and so on plus K50. If I have 50 elements, so I have to first calculate what are the element stiffness matrix for each element. Then I have to assemble all those stiffness matrix to get the global stiffness matrix. So this is what we call it as a global stiffness matrix, that is denoted by capital K, where U is the once again displacement which are there at the different nodes in the body, and F is the force which is applied to the entire body. Wherever the forces applied, that I need to consider. So once again, I given here K is the global stiffness matrix, U is the once again displacement which are there at the different nodes, and F is the global force vector. See why I use the word vector here, because it's a column matrix. Therefore, I am using the word vector here. Okay. So that is what your fourth step, getting the global stiffness matrix, or it is also called overall stiffness matrix. That is fourth step. Coming to the fifth step, there we need to apply the boundary condition. So as I told, FEM doesn't solve the problem if I apply the boundary condition. So there are two ways to apply the boundary condition in FEM. So one is what we call it as an elimination method, and second one we call it as a penalty method. So I'll tell you once again in the problem, sometimes he will mention use the trigonometric function and use the elimination method of boundary condition. Then of course you have to use the elimination method. There you cannot use penalty method, or vice versa. So therefore, what elimination method says, the rows and columns of the nodal point where the boundary condition is applied, they will be get eliminated. Straightforward, you can eliminate because you know there the displacement is 0 where the boundary condition is applied. Therefore, we are using the term here elimination method because we are directly eliminating that particular row and column where the boundary condition is applied. And second, as I told, it's a penalty method. See, you don't worry how this elimination method and penalty method, when I solve the problem, there you will have the clear picture. Only just understand that where the boundary condition is there, that particular row and column in that matrix will be get eliminated. If I come to the penalty method, in the penalty method, what happens if I have a body? What we are trying to do here is, we are if it is a fixed condition here, we are trying to model it with the spring. So what I am doing here, this fixed condition is attached to a spring, and this spring is attached to the body. Nothing but directly this fixed end is attached to the body, stating that this spring is having a very large stiffness. When this spring is very large stiffness, then when I apply the force here, then if this force will create the deflection in the spring, then definitely there will be some deflection which is there at this end. If this force doesn't cause any deflection in this spring, then as good as it is completely constrained. Are you following this? So that is what we are considering it as a penalty method, where we are considering the maximum value in the stiffness matrix, and that will be multiplied by 10 raised to 4. So why I am multiplying with 10 raised to 4? Even you can multiply with 10 raised to 6 or 10 raised to 8 to say that this spring is having a larger stiffness. But most of the time it is found suitable if I multiply with 10 raised to 4. Therefore, usually we'll go with 10 raised to 4. There's no rule that you have to multiply with 10 raised to 4. Even you can do with 10 raised to 6 or even 10 raised to 8. So that is what the applying the boundary condition, that is elimination method as well as penalty method. Then clearly you will understand when I solve the problem. Then coming to the last step, as I told, we have 6 steps. So in the last step, after you applying the boundary condition, directly you can solve for the unknowns. Like first you will get the displacement, which is there in the body. So using the displacement, you can calculate the stress. Once if you know the stress, using Hooke's law, you can calculate the strain. See, as I told in FEM, I am going to consider displacement is U. So once if I get this displacement, I can calculate the stress. How I can calculate the stress? Because my stress will be equal to force by area. So I will be knowing what is the force and what is the applied, what is the area of that body, so that I can calculate the stress. Once if I know the stress from Hooke's law, I can calculate strain. How to calculate strain? Strain will be equal to stress divided by Young's modulus. I will be knowing what material I am using. For that particular material, I will be knowing what is the Young's modulus. So based on that, I can calculate what is the strain is. Okay, so this is how we can solve any complex problem using this FEM method. Okay, so anybody is having any doubt in this up to this 6 steps? Up to these 6 steps, anybody is having any doubt? Am I audible?
Yes, sir, audible, sir.
Yeah, any doubt? Anybody is having any doubt? Up to we are?
No, sir.
Understood, no?
Yes, sir.
Yeah, now I think you have better clarity compared to the previous.
Yes, sir.
Okay, so these are the 6 steps. So try to understand these 6 steps, and you can write in your own words. Sometimes in the examination you will get a question, briefly explain the steps involved in FEM. So these are the 6 steps you have to explain. Don't mug up the things. Try to understand the concept and you try to write in your own words. No problem. Okay. So I'll move to the next. Advantages, application and limitations of FEM. So first I'll go with the advantages. What are the advantages? See, the first advantage is irregular shape bodies can be analyzed very easily. So as I told, irregular shape bodies. So any body which is not a regular shape, something, the body which is of this shape can also be analyzed, or I can also get the solution for this type of bodies, which is not possible in case of conventional, because see, I cannot apply the equation. See, for example, for this body, if I want to find out the area, how you are finding the area? See, for this body, say for example, for this body, I can calculate the area. How I can calculate area? How I can calculate area? A into B, right? Because I know the equation here, A into B. Because here I don't know how to calculate this area, because it is not a standard shape. Even I don't know what is the equation for this. So such type of bodies can also be analyzed, or we can get the solution for such type of bodies. That is the first advantage of FEM. It can handle unlimited and any kind of boundary condition. See, in conventional method, I'll tell you what is the meaning of this. It can handle unlimited and any kind of boundary condition. See, in in mechanics of material, see, in mechanics of material, if I come to the beam problem, let us consider a beam. Which kind of beam it is? Can you tell me? Can anybody tell what is this kind of beam? What is this beam? Yes. Which kind of beam it is? Which kind of beam it is? This beam.
Cantilever, sir.
This is cantilever. Okay. Can you tell me what is this beam?
Simply supported beam, sir.
No. Simply supported beam is this. This is my simply supported. I am asking this. This is what we call it as propped cantilever beam. Propped CB. This is what we call it as a propped cantilever beam, which is fixed at one end and provided support at the other end. Correct? No? I have fixed at one end and I have provided the support at the other end. This is what we call it as a propped cantilever beam. See, in case of a propped cantilever beam, if I want to get the reactions, are you following this? Suppose it is applied with the force P. How we are going to find the reaction? Can you tell me how we are going to find the reaction? How many reactions? Yes, how many reactions? In this problem, how many reactions? Because of this applied force? Yeah, 3 reactions. Because of this applied force, fixed end 1 R1, and at this I have R2, and I have a moment reaction M1. So these are the 3 reactions, right now? Yes or no? Okay. Then how we are going to solve the reaction? By using static equilibrium condition. What is my static equilibrium condition? Summation of Fy is equal to 0 and summation about any one point moment is equal to 0. These are the 2 equilibrium, static equilibrium condition you are using to solve the reaction. But here I have 2 equations, but I have 3 unknowns, R1, R2 and M1. Is it possible to solve?
No, sir.
How many unknowns are there? I have 3 unknowns, R1, R2 and M1. To solve these 3 unknowns, how many equations are required? 3 unknowns, minimum 3 equations. Right now? Yes or no?
Yes, sir.
Yeah. In this case, using this static equilibrium condition, I cannot solve this problem. But FEM solves this problem. Not only this problem, any other, say for example, if I give one more support here, and if I apply the force, one force here, one force here, if I remove this, and if I apply one force here and one force here, even FEM solves this problem because I have 4 unknowns. But only if I want to solve using mechanics of material, it is not possible because I have only 2 equations, but unknowns are 4 here. But that can be done using the FEM. Therefore, unlimited and any kind of boundary condition can be handled using FEM. Then it can handle irregular loading without any difficulty. See, we have loading like point load, UDL and UL. Sometimes if I have a body or any beam or body, if it is applied with an load of this kind, any irregular shape load, which is not possible in case of mechanics of material, because mechanics of material, I know the load which is point load, UDL and UL. At the max, I know the couple, but this irregular shape force, I don't know. Then what I need to do? I need to divide this into the nearer to the uniformly distributed load. Then I have to solve the problem. So FEM does that. So it will irregular whatever the loading, it will try to make it uniform. Then it will solve the problem. So that is what the third advantage of FEM. That is, it can handle irregular loading without any difficulty. Then coming to the next advantage, see, unlimited number of different materials like composite materials. So which is not possible in case of normal mechanics of material. So FEM does that. So any unlimited number of bodies, that is composed bodies, can be analyzed very easily. And the last one is it can handle non-linear behavior and non-linear material. See, if a material is not behaving linearly, then your conventional method is not possible to use to get the solution. In that case, so this FEM will help to get the solution for non-linear behavior as well as the material which behaves non-linearly. So that kind of means behavior as well as material, if it is there, we can get the solution using the FEM. So these are some of the advantages which are there for the FEM. Now coming to the application of FEM, so I'll quickly go through the application of FEM. It can be taken with 3 broad areas like engineering, medical science, as well as dental science. So I'll just go through the because as we are very interested in engineering field, so I'll take a broad classification under engineering field and very limited under medical and dental science. So when I come for the engineering, first comes with the mechanical engineering. Under mechanical engineering, like automotive engineering, different components of automotive engineering can be analyzed. Aerospace and aeronautics engineering, where once again the shape of the bodies which are there in aerospace industry, they are of very complex in nature. So those kinds of components can be analyzed. Even in thermal analysis can be also done. For example, nuclear reactors, very much heat is involved. Physical thing is not possible. So in that case, we are taking the help of this FEM. And any structural analysis related to mechanical can also be done using this FEM. So these are some of the areas which comes under mechanical engineering. Similarly, if I come to the another engineering section, which is civil engineering, there they are doing the analysis of the bridges, even sometimes analysis of the buildings. So all those can be done under civil engineering. Then coming to the electrical and electronics, people can also use this to know what are the electromagnetic field which is available in the circuit, whether it is feasible for that particular PCB or not. So all those you can cross verify using this FEM. Then coming to the next is circuit analysis. You can do the circuit analysis, how the effective flow of the electromagnetic field, all those you can do using this FEM. So then coming to the next application comes to the chemical engineering. So under chemical engineering, the important thing is flow analysis. That is what we call it as a computational fluid dynamics. So where we can do the analysis of the flow of fluids, flow of gases. So all those we can do it. Anyhow, one module which is there for your syllabus for the flow of whatever liquid or gases. Okay. Then coming to the next engineering field is biomedical. So nowadays, all biomedical equipments are designed by mechanical engineers. Like HCL is a company which is into biomedical. Like that, there are many what the companies are there, they are working on biomedical equipments which are used in operation theaters. So analysis of those biomedical equipments can be done. Then these are some of the engineering areas I have taken. Then coming to the medical science, the entire human autonomy analysis you can do, like what are the stresses coming on the bones. So all those things you can do the analysis on the human anatomy using this FEM, which is main area which comes under medical science. Then coming to the dental science, where you can do the tooth analysis. So you can get what are the stress coming on the tooth and all. So that is comes under dental science. So these are some of the applications of FEM which are used in wide variety of fields. Then see here I am not saying disadvantage. Now why I am saying disadvantage? Because disadvantage cannot be eliminated, but limitations can be eliminated by making a requirement. What is the requirement? If I do, I can eliminate the limitations, but a disadvantage cannot be eliminated. So FEM doesn't have any disadvantage. It is having only the limitation. So which are those limitations? The first one is approximate solution for complex problems. If it is a complex problem, I'll get an approximate solution, but still it is an accepted solution. That is one limitation. Second is analysis of complex problems required high configuration computer. So very high configuration computer is required to do the analysis of the complex problem. That initial investment you have to do, that is only the limitation. If you have the company is having that much of capital, so they can invest, and this limitation can be eliminated. An initial cost of the software is very high, because manually FEM cannot be done manually for complex problems. We have to take the help of the computer, because a lot of equations will be there. Manually it is very difficult to solve those equations, so therefore we have to take the help of the computer. Therefore software is there, it comes with the high cost. Therefore that investment you have to do initially, that is one more limitation. And coming to the last limitation of FEM is there we require the skill operators. That means see, computer, if you give some input, it will give the output. The ultimate thing is we need to analyze that output, whether the output is feasible or not. If it is not feasible, what are the changes I need to make? Whether I need to change the load, whether I need to change the material, whether I need to change the boundary conditions. So that analysis can only be done by the engineers, not any other people. So skill of the operators also matters if I am using this FEM software. So these are some of the limitations. So all limitations can be eliminated by making some proper arrangement. As I told, it is not having any disadvantage. Okay, so these are the application, advantage and limitations of FEM. So now it is already 12:40. So this potential energy and principle of minimum potential energy, I'll continue with the next class.